Hi friends, welcome to the channel Learning R is Fun. In the last two videos, we have seen the linear regression with certain examples. We will continue our discussion in this video with multiple linear regression. The equation of the multiple linear regression is shown on the slide. Basically, you can see the intercept, which is beta naught, and then you get coefficients for each of the independent variable, that is x1 to xi, beta 1 to beta I. These are the various coefficients. This is a simple straightforward equation, and the equation can become complex also. We will see them in another slide. Now, when we specify a formula, a model formula, so far we have used plus. Plus basically means the first term plus second term. When we say all the terms in the first together with all the terms in the second. As an example, we have got MPG as a function of weight plus HP plus drat. It doesn't mean the arithmetic addition here. It means all the terms of weight, all the terms of HP, all the terms of drat have to be taken into account while doing the relation. But apart from this plus, we have got certain other symbols. One is colon, another is a star or asterisk. The third one can be the exponential, that is a cap symbol. But each has got its own meaning. When we say first colon second, it indicates set of terms obtained by taking the interactions of all terms in the first with all terms in the second. And exactly how the equation will form, we will see in the next slide. Similarly, for asterisk, that is multiplication symbol, first multiplication second indicates the cross of the first and the second. This is same as the first plus second plus first colon second. Okay. Then we have another form also, that is first plus second, the whole exponential 2. Here it indicates order and not exponentiation. So this raised to the power 2, like that we should not think. So all these things are explained in the next table. Here you can see the first one is very simple, straightforward, which we have been using. The second one, when you don't want the intercept, you have to say y as beta 1 a. While specifying the formula, you have to specify y as a function of a with minus 1, that is without intercept. Okay, suppose you want a square to be used, then you cannot put a plus a square, you have to use identity function, and then within that you have to say a square. So if you say that, then R will make that understanding and say beta naught plus beta 1 a plus beta 2 a square. But if you are simply using the exponential, like in the last case, a plus b plus c, then exponential 2, it simply means a, b, c separately, and then a, b, b, c, c, a, 2 at a time. Okay, you have seen that. So there is no ABC here. When you are having, let's say, a colon b alone, then that means only AB, not A and B. When you say A star B, it means A also, B also, A colon B also. That means A B also. So how the terms should appear on the right hand side, which coefficients have to come up, is depending on all these combinations. But depending on circumstances, we use a formula that requires a domain knowledge. With the domain knowledge, you may be able to form the type of equation you want. The relationship you are setting will be based on some intuition and then some domain knowledge. See, we have got two examples here. Y beta naught plus beta 1 x1 plus beta 2 x2 etc. beta k xk. This is also a linear equation only, multiple linear equation. The next one is also a linear equation because that form is there. Coefficient, then independent variable. Coefficient, then independent variable. Okay. Now in today's session, we will be dealing with a cloud seeding example. So here basically I have given this slide just to give an introduction to it. Rain is the dependent variable, and you do the cloud seeding with the silver iodide. And when you do that, SNE. S is the suitability, N is the number of hours between 1300 hours to 1600 hours GMT within 10 centimeter echoes in the target. Then you require a cloud cover, then pre-wetness and echo motion. All this cloud cover and EM you check by radar, and pre-wetness is the rain just prior to your seeding. So with this kind of inputs, you have to form the regression equation, which is multiple linear, and you have to predict the rain. Now let's go to RStudio and do some coding. We'll start this session with the stack class dataset, and it comes to the base R. We'll ask R what is stack class, and we can see here a stack class is basically a data frame with the 21 observations on 4 variables. These are the 4 variables, and stack class is the dependent variable, and these are independent variables. So basically obtained from 21 days of operation of a plant, where these 3 can be controlled: airflow, water temperature and acid concentration. And then what you get is the output in nitric acid from base material ammonia, but there will be some loss. Basically it is going to tell us the efficiency of the plant. Okay, now what we'll do, we'll create a model, stack class as a function of other 3, a straightforward formula. So we have created the fit. Now fit.sl can also be obtained simply by saying lm function stack.loss as a function of other 3, whatever remaining variables are there. That too, so without mentioning them, we can put them as a simple dot. That also gives the same thing. Now we have got a problem here, that is predict the stack loss if the airflow is 72, water temperature is 20 and acid concentration is 85. These 3 values are there. So we can, first of all, we'll create these values we'll create in a data frame. So data.frame will create the 3 variables where we'll mention these values, and then this data frame will store in new data. So we have done it. Now we can ask what is new data. We can see in the environment also. We can ask what is new data. It's a data frame. Airflow is 72, water temperature 20 and air acid concentration 85. So let's close this. Now we can ask predict. We can use predict function, and we have to tell the model and the data. So we can do the prediction. Done the prediction, it is coming to 24.58173. That is based on the multiple linear regression model and the given parameters, the predicted stack loss is 24.582. So it's a straightforward multiple regression case. Let's do one more thing with a little bit complicated case, that is cloud seeding. Now before that, let us remove this. Okay, and history also we can remove. So we'll keep this as empty. Okay, this also we can keep here, and there is a plot here. Okay, we'll start off cloud seeding. So there is a library package HSR. So we have to do library HSR. You should install it if you have not done it. After the installation, you can see clouds. What is clouds? So clouds is a data set as a part of this HSR package. Let's try to understand. Data from an experiment investigating the use of massive amounts of silver iodide 100 to 1000 grams per cloud in cloud seeding to increase the rainfall. In extremely dry areas, cloud seeding has been tried, and this practice has helped some precipitation in those areas, that is the rain. And the variables are here: seeding, that is a factor indicating whether the seeding action occurred or not, that is no or yes. Time, number of days after the first day of the experiment. SNE is the suitability criterion. This suitability criterion is arrived by finding the cloud height, etc. And then cloud cover, basically you get radar measurement, so you get this. And pre-wetness, that is the total rainfall in the target area 1 hour before seeding. Echo motion, again through radar when you see whether the cloud is moving or stationary. Rainfall is the dependent variable, that is Y, the amount of rain in cubic meters in times. Okay, that is rain and then time. So therefore rain time is the unit. Now let us write the, we can see some data. So we can say head clouds fly. So we can have a glimpse of that data. So seeding we are getting no, yes, etc. And pre-wetness and cloud cover, SNE, these are values. Whereas eco-motion is a factor. Again you can say it's a stationary moving, so it can be made as a factor. Seeding can be made as a factor. Okay. Now let us write the clouds formula. The clouds formula by domain experts. They have done all the research and finally found this formula is appropriate. That is, rainfall as a function of seeding. Seeding has to have interactions with the other four. That is SNE, cloud cover, pre-wetness and eco-motion. So that's why this interaction symbol is given. And then time is also to be taken into account. So that's the formula. And this formula will give a specific betas as we have seen in this slide. So in this case, let's make the formula first. Then before going to model, we must understand what is a model matrix. See, in normal, in all the earlier cases, whatever you have seen, we got the model straight away. Here also you can get the model straight away. That is your, you can see here. This is the model. LM, clouds formula, data is clouds. So clouds underscore LM is what is the model name. If it, you can say. And before that we have seen this. This is because in this case, we are seeing some interactions here. So let us, before going to the model, let us see what is this matrix. This model matrix, model.matrix is created by R with certain dummy variables based on our formula. Okay. Now you can see model.matrix creates a design or model matrix, and by expanding factors to a set of dummy variables. If you read this, you may not fully understand, but you can see easily understand it with an example. So what we'll do, we'll see the model.matrix, which is created internally when you create a model, but we can also externally create it using model.matrix function. And the formula you have to give, data you have to say clouds. So this will store in X star. And now we'll look at X star. Environment, we'll see what is X star. Okay. Now you are able to see it's a data frame again. Here you have got intercepts and then seeding S. SNE. SNE is the criteria which is there in the clouds structure. So straight away the same thing you got here. Say you can see here. Structure of clouds. Okay. This seeding is coming out here but with S, because there is a no and S here. So if it is no, the original data is no, then you got 0 here, because you are saying this is seeding S. Seeding S, when there is a no, then you get it as 0. When seeding has taken place, you get this as 1. Like that, this has been created. SNE is straight away simple copy of the same column. SNE 1.75, 2.7, so the same values are here. Cloud cover, same. Pre-wetness, no issue, same thing. But when it comes to eco-motion stationary, eco-motion is the actual variable. But moving or stationary, there are two variables here. So it has taken eco-motion stationary as a variable name, and in that it has taken 1, 0 like that. So when it is stationary and you are saying the heading as stationary, therefore it is 1. When it is dynamic, that is our moving, here you are saying 0, because eco-motion stationary is false. So you are getting 0. So like that, the model matrix is constructed using dummy variables based on the formula. This is what you can understand. And this model matrix is something which is being used to create the model. Okay. Now this is behind the scene, but to get an understanding, we have done this. Now let us create the model clouds underscore LM. Now let us look at the summary. So here you can see the coefficients have been created accordingly. seeding S, SNE, cloud cover, pre-wetness, these are straightforward variables, factors, or you can say the predictors. But here a new predictor has been coined, co-motion stationary. And another is seeding S, then SNE. There is an interaction here. Seeding S, cloud cover, like that. So when you got this many various predictors created, and for each of them an estimate and then standard error t value has been found out. And then you find finally the probabilities. When you look at the probability, you find seeding S is significant, and then seeding S with SNE is significant. And other three are okay, somewhat closer. Remaining factors are of no use. That's what you understood from this. And overall the model is less than 0.05, so it's okay. And R square, only 50% you can say of this model explains only by 50% of the variability. That means the model could have been better. So further tinkering may be required. Okay. This is the understanding of this work here. We can also have some visual understanding. So what we'll do, first we'll take the seeding and then convert this factor into a numeric. So we'll call that as CS. So as numeric, clouds underscore dollar seeding. Now we'll create the plot. Rainfall as a function of SNE, that is the criterion. Data is clouds, and point, the type of character to indicate the point, 0, triangle, square, etc. That will save, that will take as CS. The type of characters to indicate points will be depending on this. That is cloud seeding. If it is done, you will get a symbol, otherwise you will get another symbol. Then next lab is the title. So got this, and then you got a circle and a triangle. We'll create one AB line, that is the linear regression line. Rainfall as a function of SNE only will do. And then one for the data which is subset as seeding is no. That is, this line is only for without seeding, and this line is for with seeding. So we have got two lines here. So we'll make a legend also. Now let us look at this plot. See, this solid line is for no seeding. So with seeding, you have to see the dotted dashed line. So this is with seeding. Okay. The SNE criterion values are here. So when the SNE criterion values are increasing from say 0 to 1.52 etc. When this criterion is increasing, with cloud seeding you get better rain. Without cloud seeding you get this rain. The rainfall is more in case of cloud seeding. So when you move on like this, at some point of time, when the criterion is beyond 4, then if you do the seeding, you get lesser rain. Otherwise, the rain is better. So don't do seeding when the criterion is above this. So in this period, this is the window where you can do seeding. When you do seeding, you get a better rain. So this is what you understand from this entire exercise. We have now come to the end of today's session, and in the next session we will be covering logistic regression. Logistic regression basically will give an output yes or no, or say to choose between male or female, or it can be a pass or fail situation where you don't want a value but you want a result, either this way or that way. Your normal linear regression will not help. So how to go about doing logistic regression is what we'll see in the next video. Thanks for watching, and see you in the next video.